In this video, we're going to write a generic transfer function that lets us model the dynamics of almost any amplifier. We'll analyze the details of this model in future videos. I've included a rough sketch of our midband response in this figure. It's a simplification because I'm only showing one zero at the origin, which is responsible for this rising slope, one dominant pole at low frequency, and one dominant pole at high frequency. In reality, there are more poles at frequencies above omega minus 3 dBH, and maybe a few zeros. And there are more zeros and poles at frequencies below omega minus 3 dBL. That's because there are a lot of caps in amplifiers, at least 2 per transistor, and each of those has the potential to create a pole and a zero. We'll include those in our equations, but I haven't opted to draw them for reasons that'll become clear in the next video. We can represent this mess of poles and zeros by multiplying each individual pole or zero term together. The big trick with this transfer function is trying to separate out gain and dynamics, which means that we have to guarantee that the two dynamics terms, here and here, are 1 in the midband. So the term on our very left is our midband gain. That's also sometimes called our DC gain, because lots of real amplifiers aren't AC coupled. The term in the middle represents our rising slope on the left of the figure, which comes from our coupling network impedance dropping and our bypass capacitors starting to be lower impedance than the resistors they're in parallel with. And we model that by imagining we have some number of zeros m at the origin, and then an associated pole for each of those zeros at locations pz1 through pzm. We have this big product of 1 over pz1 to pzm in the numerator in order to make sure that this term is 1 in the midband, because as s over pz1, for instance, gets bigger than 1, s will cancel with one of the s to the m's, but we need the pz1 to cancel with something for the whole thing to be equal to 1. It's also worth noting the zeros don't all have to be the origin in a real amplifier, but I've put them all there in this generic transfer function for simplicity's sake, and that works okay because we know at least one of our zeros is at the origin from our coupling cap, since no DC signal can get through just the big series capacitor we put in front of our amplifier. This term on the right represents our high frequency roll-off, and it consists of a bunch of poles at locations P1 through Pn. There could be a few zeros in here, but I've opted to omit them because this big generic transfer function is skimping on a few details. I've used n as a subscript here to show that in general the number of high frequency poles is not equal to the number of low frequency pole zero pairs. We're going to rewrite each of these terms in a slightly different format. I've written the high frequency poles in terms of their time constants instead of poles, which is easy because each tau I is equal to 1 over pi. I've also opted to rewrite the low frequency pole zero pairs in canonical form instead of factor form, so each individual pole zero pair is represented by s over s plus p. This is a weird choice for me because I think factor form makes frequency analysis much easier usually, but this canonical form will be useful in the future. Finally, we're going to distribute the denominators, which will help with some approximations we're going to do later. And that's it. These are all the representations of our midband that we're going to use. But big picture, there's a midband or DC gain, a coupling term that represents our low frequency pole zero pairs, this rising edge that eventually flattens out, and a roll-off term that represents all of our high frequency poles. So in summary, we can estimate bandwidth by finding the dominant high frequency and low frequency poles in our overall transfer function, which is why we get this midband shape. The general transfer function for an amplifier with a midband has a DC term, low frequency dynamics, and high frequency dynamics, and those are represented here in these two representations that we're going to use.